Good afternoon, everybody. I'm actually recording today at school, so if you hear the bell ringing right in the middle, that absolutely could be happening, or the door slamming behind me. I apologize for that. But today it's going to be a short little lecture. We are going to talk about how to measure this heat that we are trying to calculate. So we talked about the first law of thermodynamics, where the energy is remaining constant in our universe. And we always have them happening in pairs where we have endothermic and exothermic reactions. Well, how are we going to measure that? And one way that we can measure the amount that is heat is released or taken in is by calorimetry. So you've done this in general chem. We did, if you remember, the barium hydroxide octahydrate lab. It was a big formal lab report, 100-point thing where you worked with your lab partner and you had to type up the whole thing, write the lab procedure and everything. That's calorimetry. So it's a heat capacity, it's a measurement of the substance's ability to absorb heat energy. And if you think about this and apply this to like water and sand and air on a nice hot summer day, which would be great if we had that right now, you can imagine that if you walk across the sand, sometimes it's really hot because it is absorbing the sun's energy. But if you hop into water, like the the river or lake down at Prescott Beach, it's going to feel a lot cooler because it takes a lot longer for that water to absorb the heat because it has a higher heat capacity. Again, our air, we can have here in Minnesota, we can have really warm temperatures, and a couple hours later the temperature drops. Well, that's because our air cannot hold in that heat, so it can change very quickly. The heat capacity of water is very high as compared to a lot of other substances. So if we talk about the specific heat is going to be measured in joules per gram degree Celsius. And if you remember, for water, let me grab a pen here, if I talk about water, that the heat capacity of water is 4.18 joules per gram degree Celsius. It's a very high value. You look at a lot of the metals like aluminum, it's zero point 0.9. So the heat capacity of water is great, and that's why it takes a long time when you're trying to make that pan of macaroni and cheese because you're really hungry. It takes so long for that water to absorb heat and get it into a boil. Now, another way that we can measure is molar heat capacity if it's expressed in joules per mole degrees Celsius. It's just a different way, changing the grams into moles. Now, for both of these, you do need to remember that they are measured under constant conditions of pressure and volume. So they are always going to be constant. All right, I guess I didn't need to write that. So there is the specific heat of water. You can see that it's 4.18 joules per gram degree Celsius, and 1 calorie is 1,000 small calories. This is the value that you see on your food labels. And if you remember the formula that we use is the change in heat, or the change in enthalpy, is equal to the mass times the change in temperature times the specific heat of a substance. And remember that this is saying that energy is going to be related to mass. Because if we take a look, this is in grams, our temperature is going to be in degrees Celsius, and our specific heat is in joules per gram degrees Celsius. So if you take a look at all of these, units are going to cancel out, and our unit for heat is going to be into a joule. Now, this should make sense to you if you think about filling up a whole bathtub of water and you want to heat it up. A teeny little coffee cup of boiling water is not going to change that. So yes, it is correlated with the mass. So this is what our calorimeters do. 2 styrofoam cups is exactly what we did in general chem. You remember, we are in chemistry, we are going to be the system with whatever you have in here that you are measuring the heat of is going to be our change in system. So you are trying to measure the difference in the heat with whatever chemical reaction you are putting in there. Obviously, something that has a lot of exothermic energy release is not going to be held in by our styrofoam cups. So things that like TNT and other things that explosives, pyrotechnics, they are studied in a bomb calorimeter, which is reinforced, as you can see here. So it doesn't matter if we are studying the amount of energy released from gasoline, from the food that we heat, or bombs, or whatever kind of material it is, we are able to measure it. Okay, some common specific heat capacities. You can see that water is very, very high as compared to the other substances that we have here. I think I mentioned aluminum as 0.9. There's something a little bit more specific with more sig figs. Okay, so if we take a look at this sample here, I want you to go ahead and see if we can do it. It is one that I also will discuss in class, and the final answer you want here in kilojoules per mole should be 24.1 kilojoules per mole. So see where you can get with that. We will discuss this one in class. And then the last thing that I want to talk about here is that standard enthalpies formation, the change in heat of formation at standard state. And this is what this means. Delta means change, heat of formation, HF, and then the little degree sign there means in standard conditions. So it's a change in energy that accompanies the formation of 1 mole of a compound from its elements in their standard states. Remember, standard states, 25 degrees Celsius, which is room temperature. Our periodic chart is referring to these. You also have standard states on a gold sheet that I probably will have already given to you. And so these are standard states. You have these on your gold sheet where we do product minus reactant. We did all of this in general chem many, many times. If you remember, it's going to be the products minus the reactants, the summation of everything. And so remember, if I end up with my enthalpy, my change in heat, to be a positive value, the energy is endothermic, being absorbed. And if it's negative, it's going to be exothermic, where it is going to be released. Okay, I think that ends up where we're at. We are actually going to do this thermite reaction, and we're going to compare this. We're going to do it as a demo. We're going to compare this to a Snickers bar. So that's what we're going to take a look at in class one day this week. So I will be assigning different problems associated in each of these parts. This is chapter 6. We are done. We're going to do one problem with Hess's law in class. Other than that, we are good to go. I hope you have a great day. And guess what? The bell didn't even ring yet.